for the introduction. I see a lot of people are here, so but even a smaller audience is okay. Before the name of the talk I give is a real-world use case. I wasn't able to give it a better name, a more appropriate name, because the customer gave me the okay that I can use their product and show it here last minute. So I will talk about what it's actually about in a few minutes. Usually we start, or I start my talks with, okay, giving a presentation who we are. John did it already. I'd like to take a minute to give a short testimonial about the OSGi Alliance, because as John said, it's now 2 years since we have joined. And the experience we had with the Alliance is great. There are a great bunch of people working there, working on the specs. And I would give anybody who is really interested in using OSGi or is already using OSGi to get involved with the Alliance. Not only solely for the purpose of working on the specs and giving your input there. It's also a big pool of knowledge just being at the face-to-face meetings, taking part in the expert group to get deep insights, and the things we've learned over the last 2 years about OSGi and how to really develop OSGi, even with the knowledge we had before, increased immensely. And the project I want to show is one of the results. So the money we invested for our membership is the one investment I've never given a second thought, because it's a great investment. So everybody, they should join as many people as possible. So even if you don't participate in giving own Rs, start own specifications, you can always give your perspective, your use cases to the specifications we are currently talking about, because we don't pull them out of thin air. So the more input we get, the better it gets in the end. So, but to the actual talk and the actual project I'd like to show you. We have a customer for a couple of years now called Radio.net. Radio.net, so to honor their involvement and allowance to tell us here, they're a radio stream aggregation platform, and for web radios, general radios, and podcasts. They are one of the biggest, at least in Germany, and also not that small worldwide. They have brands in 10 countries, more than 24 languages are supported. They know about over 40,000 stations worldwide, and the count is going up. So they're currently moving towards adding more podcasts, becoming more of a podcast platform with 400,000 podcasts they want to add in the near future. Also, the countries they support will grow. So currently it's 10, and by the end of the year it will be 20, as far as I know. So they have about 7 million unique users on their website alone, and 27 million app downloads worldwide on Android, on Apple, and many other platforms. And also have integrations for things like Amazon Fire TV or Echo, Google Home, also the Apple version of the stuff. And this is what the project is actually about. I want to show you. But before I go into this again, a brief history how we got together with Radio.net. A couple of years ago, they made a big relaunch of their website and hoped to get rid of some technical debts they had there. And one of the pain points they had been their search and indexing backend. They used the Solar before, but nobody really knew how it worked. We already had some experience with a direct Lucene implementation for our RCP stuff we did at the time. And so we convinced them to get a custom-made Lucene-based backend. At the time, and still is based on EclipseCon. I'm not quite sure if somebody knows about it. It's still a PDE build, so the old server, because since it's running, they also they only had money to get new features in, but not to give us the time for a major refactoring. In front of this, they have a Tomcat monolith at the moment, which is the API to their backends, and especially the search backend, which drags through all the requests, asks the search backend, and then gives the stuff out. And yeah, Radio.net is currently undertaking big efforts to get rid of the old Tomcat monolith, because it's a huge mess, and so they really see the point of going away, moving more to microservices and Docker. And I'm working on them to base many of their things on OSGi. And just that you have a feeling what RadioDE or Radio.net looks like. So their homepage looks something like this. So, and everything when you search something here, this goes through the search server, same as here. Every list you see somehow is produced by the search server. So the only database access in the end is when you go to a station page and then they say, okay, now get it by ID from the database, and everything else is done by our server. So what's the goal now from what we have here? The thing is, as I said, they have implementations of they have apps for Amazon Echo and Google Home, so voice-controlled devices, and search by voice has different needs on a search than than typing somewhere. So if you type something, it's more like you're on Google, you can type things, okay, I want this specific station, or you can type something, I want rock in Hamburg or rock in Ludwigsburg, so you have different contexts for your search. But on a voice search, you don't have any ability to browse a list afterwards. So you go more like, okay, play for me Radio Energy. So and then you should get Radio Energy and not something which is radio or Radio Hamburg, for example. So and you don't want to get any radio stations from Hamburg, but this specific radio station, which is called Radio Hamburg. So therefore, we had the point that we wanted to, so they wanted to implement this in the old search server. And I said, no, you want to move to microservices, you want to do it to new technologies, so I will rebuild the old search server in a smarter way, using all the R7 specifications we've learned about, using BND instead of PDE, to get, in the end, a smaller, more specialized version of the big search server we have for them. And yeah, this is what we started with, the old search server. Like I said, Equinox, Gyrex-based PDE and Tycho build. We heavily use EMF for the data models we grab from the database and we use in the API. Also Lucene, a pretty old version, the version 4.8. Wrapped around this, we had our data in motion search framework, which can take EMF objects and map them to an index. And underneath it, MongoDB as a general data store for the raw data to rebuild the indexes from. I will not go too deep into Lucene during this talk because Lucene could fill a whole day in and of itself. So I will just mention the brief things that are necessary. So the new voice UI search component or the search application will now be based on Felix, built with BND. From the current R8, R7 specs or the main specs we are using, this is the JaxRS Whiteboard, PushsStreams, the configurator. Together with this, we have our my rebuilt version of the data motion search framework, now under the name of Gecko, an open source project. I will say a few things at the end to this. EMF in a plain OSGi way without all the Equinox specific stuff EMF has, so this is called Gecko EMF. Still Mongo database as a data store underneath it, and Docker. Who knows about Lucene? Lucene is currently at version 7.5, but they switch their versions faster than I can switch my underwear. So they're going faster ahead than Firefox does. So keeping up with their version changes is kind of impossible. So we stayed with it's actually Lucene 6.6, I believe, not 6.8 we're using. But nonetheless, so before I show you what it actually looks like, just to give you an example, fits quite nicely to the previous talk. This is the workspace with the old search server, which in fact provides the same functionality as the smaller version does. It just has a few more queries and calls. So the actual components are similar. So and this is what it looks like built with BND. So everything else is just overhead produced by PDE and produced by using features and P2 update site and target platforms and so on. So let's see what it looks like. To give you a glimpse of what it is. So we start out having our data model defined because I'm not quite sure what you know about working with Lucene or working with indexes. Usually you use it, Lucene is like a database with a flat structure where you do all the things you usually do in a database on search time at indexing time, meaning you do all the preparations to have everything pre-calculated, that when you search for something, it's immediately there without any real calculation. It's just looking up where everything is. And RadioDE has a station object. I hope it's readable from back there. The station object itself is relatively complex. There's name, latitude, episode names, if it's a podcast, topics, genres, and all of these objects and all of these text fields are a list of translations in the end. So every object contains 23 or 24 translation of every conceivable thing you have in there. And in the end, somebody does not need every translation. They just say, we want it in German. So what the index, what we do on index time is we take the station apart, create multiple instances of the stations with only one language in it, and this is what lands in the index. So you have a document in the index with the name in German, for example, with the description in German, and so on. So all the fields you need. And later at search time, we say, okay, give us just results where the language is DEDE, for example, or FR, so the local code. So, and in the end, after the search, this is what the result is, what the user or what the API expects. So we have our search result, which just can contain a list, but usually contains just one result with a name, the genres, and the stream URLs where Echo or whatever is using it can instantly start streaming whatever is available there. How does it look like? In between, we have the first thing we have is the JaxRS REST. Here we are, the REST endpoint. Shitty mouse. The REST endpoint, which uses the JaxRS Whiteboard. In this case, we use a meta annotation telling the system that we need our search REST runtime containing of the JaxRS Whiteboard. In this case, we use an own implementation, also available as an open source implementation called Gecko REST. I will give you the links at the end of the talk. Give it some properties that we want to use EMF for the serialization and deserialization. And it simply delegates the parameters you give to the Alexa search service, which then wraps the Lucene, is doing the search for you, returning a result, and this we return to the customer. So, and it's only in the end 3 different searches they do. The one is just search by name. Then they can distinguish by, so Alexa, for example, allows you to distinguish to get things like, okay, search radio energy in Munich. So then because of the in, he knows, you want to search in a location. So, or you can search something like by, they can distinguish between genres and stuff. So this they can predetermine and tell us there. In the end, the results can look like the following. We just, where is my reeling bundle? Here we are. Here we are. I don't like my mouse, or it doesn't like me. We're gonna run it. Takes a second to start. I have no idea why it takes always this thinking time before it starts up. So here we go. So the first thing the server is doing when it starts, it looks what the state of the index is, because we have the source data is in the database, the Mongo database. This is fed by the old search server. It gets the updates from their Tomcat backend if something changes, somebody changes something, transfers it, sends it to the search server. The search server puts it in the index and also in the Mongo database, and this is where we are coming in here and say, okay, we just, on startup, we need to look in the database if there are changes. So, because no idea when the last time was the search server was started, or this version of the container was started, so the index can be stale. So we have to check how many documents are in the index. Are there new radio stations? Are there updates on the radio stations? They give us a last modified date, and we take all the stations from the database, go over the index, compare if there are modifications, and then handle it accordingly. And this is where it becomes interesting, because there we use PushsStreams, but I will show you this in a minute. In this case, I had a preset build index for you because it will take a few minutes to do all this stuff. And it's quite heavy on the processor. So it says, okay, we have 55,000 stations overall in the database. None has changed. We have to do anything. So the service comes up. The Alexa search service states that it's ready. And then it can be picked up by the search service, by the REST endpoint here. And because it's a mandatory, reference, this is the time when the actual REST endpoint becomes available. Beforehand, nobody is able to search anything because there will be no endpoint for it. So this you can see here in this log message that Jersey picks it up, or our implementation picks it up here and adds it to the application we are using. So we can try it out. Have a voice UI search here, for example, and we want to search for a station near where I'm living. Sorry, this is the wrong one. MDR jump, this is a station near my hometown, and it gives us, oh, MDR jump. So this is what it's doing in the end, delivering quick and easy search results for the thing. Usually the response time is a couple of milliseconds, so it's not too much, and this is what an index is for. So now to the other, what kind of other specifications are we using here? The one thing is the configurator. Before I to show you, we have to configure, for example, our index. So, and this is done with the configuration, the new configurator, which is just placed in the bundle, saying, okay, this is our Lucene indexer. This is the kind of file system it should use underneath. It's some Lucene specific thing. We represent it all with services, so and this can be configured here quite easily. On startup, it is pulled in, given to config admin, and then configures our services that needs to be provided back there. The same thing for our database. We have the ability to save EMF objects directly in Mongo database, and this is also configured via the config configurator here. So, and the best thing was, this is one thing where what I said initially, that the OSGi Guidelines gives you access to a lot of knowledge. So as I was playing around with it, we had been in Sofia at a face-to-face meeting, and Tim was there luckily and gave me a hand in optimizing the PushsStreams stuff. What this service does, when it becomes active, it's at first says, okay, we have an index state. It registers as a service that says, okay, this is unchecked at the moment because we are getting up the first time. So, and then it says, okay, we need a first index build. So usually you would find this here with a false inside it. False would say, okay, we start from scratch, we drop the old index and start a new and index everything from scratch to make sure no changes in the structure have been happening since our last start, because this could be the start after redeployment, for example. So what it's doing then, in our case, we have this mechanism that differentiates. What I do is, instead of dropping the index, which would be done here, I go to, give me a second, I have to see my own, from my own things here. Query builder, where is it? I missed. Check index, yes, the check index method, this is what it's doing. We have the ability to get from the Mongo database a push stream, because in many cases, if you load huge amounts of data, the database can provide it fast or slow regarding how big the objects are. So the objects come in on actually mostly a fixed rate, but in the end, they aren't available immediately. So you don't have a list you can iterate. Also, you would get out a list after it has finished loading. But MongoDB, for example, has some streaming mechanism. So it loads the objects, has some kind of internal cache, and you can iterate over it. So if you are faster iterating over it, then the iterator waits. What we are doing here is we provide a push stream, which gives us the objects as soon as MongoDB has read it from the database, puts it in the push stream, and then we can use them. This has the nice ability, if we use these objects and are slower in processing these objects, what indexing, for example, does, it needs quite some time to do all the processing and the calculations. we can use the pushback mechanism to say, okay, guys, it's too much for us, be slower. So then we tell the Mongo client, okay, wait a millisecond. Next round, wait 2 milliseconds before you give us the next object, and so on and so forth. So you get a nice streamlined memory footprint there, because the moment stuff got indexed, we can give it to the garbage collector and say, okay, now you can do your thing. And this really increased the performance of the indexing itself. In the previous version, in the current version of the search servers that are running, full index needs roughly half an hour. With the new version, we got it down to something like 4 to 5 minutes in this case. And before we used up all the memory the servers could give us, 24 gigabytes on a productive system, and here it runs smoothly with 4 gigabytes. So because the handling and cleanup is much, much faster and much, much easier. So this is what you can see down here. Give me a second, I have to find the right method where we did all the configuration magic. Here, this is what we did here. We have our PushsStream provider which creates the PushsStream builder. The PushsStream builder says, okay, we have a pushback policy. The pushback policy calculates itself on the queue or on the cache it has. And it says, okay, if there are more than 650 objects in our cache, start with the 651st object to give back a 1 millisecond delay. If the 652nd one is in there, then it gives back, okay, wait 2 milliseconds until we grab out the next batch of 600 objects and index them. So this makes it quite easy to use and has a nice performance increase. So in the end, we use things like, for example, okay, now we have our stream, split our stream. According to a rule, if the station, for example, is new or the station is to update, so we split it into 2 push streams. One is to index the things as new objects, and the other thing is doing the update on the index. So this is what's been done here. Then we get 2 streams out of it, in this case in form of an array. And then we can finally say, okay, we do a coalescing. We want to have a batch every 600 objects on this thing, and in the end, call the batch update many on the index. So this is what it does here. PushsStreams themselves are one of the most powerful tools. How am I on time? 10 minutes or 10 minutes roughly? Okay. PushsStreams themselves are a quite powerful tool, but they lack a bit of documentation. So it's, but it's worth putting the effort into it, because Tim had talks about it for the last years. So, and it's really worth having a look at it, especially if you do mass data. So do work with huge amounts of data, especially if you can get it connected to a database. So, and in our case, for example, the old search servers had a mechanism to, they got a push from the Tomcat backend with an update for the station, and then they propagated this update to all the other nodes of the search servers, and then everybody picked it up and updated the individual index. So, and in our case, this was done with a kind of remote event admin, and if you could pick this remote event admin up here as well, and just give it as a push stream, and you can give it in the exact same logic here and say, okay, one other source is not the database, but the other source is our event admin or a remote event admin, which gives you the object. So you can then use the same mechanisms with the caching, with the, okay guys, make it a little bit slower and so on. You can use the same mechanisms without reinventing the wheel all the time. And this code block here, which looks quite complex because I've implemented the okay, if something changed, then do an update or index it as new or delete it, which wasn't available in the old server. Basically, the lines of code to create a new, to index the new, a completely new set of stations became a couple of, like 15 lines of code in comparison to near to a couple of 100 lines of code it has been before, as I was using the Eclipse Jobs API, for example. So this is a short overview on what is done here and what can be accomplished in a relatively easy manner using BND and also the latest R7 specs. One of the things I realized while I was developing this, I had, for example, I had my workspace like here running my launch configuration for 6 days straight without even restarting it, and was developing, putting in new stuff, testing stuff, and I've never really realized that I actually never restarted my launch configuration there. So something that was impossible before. And this is the power what R7 gives you on the way. So back to my presentation. The customer, as a Radio.net, also has other plans for the future. So they have a concept called backends for front ends. So meaning they have their Docker cluster with their Docker images and their microservices in it, and they want that nobody should be able to talk to a service directly. There always should be some layer in between, which provides a specialized API, for example, for a mobile app, for the Alexa, or whatever the purpose in the client is. So in this layer in between, some piece of software should then consume the internal APIs and the internal services and compose the result that the actual client needs there, which is kind of a sensible approach to do it this way. But at the moment, they are heavily relying on Spring and stuff like this. And as I was looking at it, it rang a bell. So maybe it sounds familiar to you as well, because what they try to do in the end is remote services. So, and this is what I realized as I was looking at it, that I have the perfect example here to show them, okay, it's already done. You don't have to do anything, because when we go back to our example here, we have our resource, our JaxRS resource, which just consumes one service, the search service. So, which can be their gateway to the outside world. And the communication to the search service can be remote. This can be somewhere, wherever you like it. So, and at the moment we are working on an own implementation for the remote service admin spec called JaxRS, which hopefully will be release ready in a couple of days or a couple of weeks at the latest. And I just thought, okay, just give it a try. So, and this is what I will show you here as a short demo. What else can be done here? So we start by starting our local version, so which is a dumped down version. Which only contains, when it's there, you will see here this topology manager, the stuff from RSA. And next to RSA, the only thing we have in here from the search thing, for some reason the search dependencies are still in here. But where's Alexa? Does anybody see RSA provider model? Alexa. Yeah, we have the index API containing the iAlexa search service, the iAlexa search service. And the other thing we have in here is the REST endpoint. These are the only two bundles. The rest of the stuff shouldn't be in here. So there's a resolution error from my side, but there's no implementation of the API we have here. So, and on the other hand, I have a Docker running somewhere back here. Hard to see what we have here. So this Docker container has is a simple container containing the remote launch agent of BND. So this, in fact, is just an empty framework based on a Felix, and has this one bundle inside it, and maybe the Gogo shell. I'm not quite sure, actually. And what will happen in the end? So after this is some old logging from previous tries. Windows takes some time to process all the logs stashed up here. Okay, obviously too many logs. Okay. Hours later. Maybe if we don't show it, it might go faster. Nope, it doesn't. Ah, what the hell. So we give it a second until it runs through there. So what I will do, I will start a remote connections session from BND, connecting to this remote agent in the Docker container. Then saying, okay, this then will push my bundles in my local workspace to this remote container, installs it in the framework, and everything comes up on the fly. Which is, by the way, a cool way of developing things, because one of the things I stumbled upon, I was finished, everything was working locally as it should. So in the installed version, and then I put it in the Docker image, started it up there, and suddenly it wasn't working as expected because the memory settings had been different, the process, also the amount of processing power it had available was different. So I was thinking, what's the problem here? So I built this version, deployed it in the Docker environment, and suddenly I could debug and develop in the real environment I'm in, usually. So this is something which is hard to do with, what the hell is he doing here? It is hard to do with anything else, and makes a quite comfortable way to developing microservices in the end. So we will ignore the logging here, so I will just start it so we can get finished at some point. So I have another launch configuration which is here for the remote development. This one just so you can see contains in the run bundles. Run requires is all these remote service things we base on the RSA. And it says, okay, the only thing from us is the index implementation we want to have here. So in the resolver in the end, shows, okay, here the Alexa API model, the Alexa, where's the rest? Alexa index API, the index impl, but nothing with Alexa REST in here. So it does not know about it. So here we are, finally. So when I start this, remote dev will be done in a second. We'll break afterward anyway. So here it starts deploying our stuff. In our case, we use MQTT as a message transport in between for the discovery and also for the remote service communication. And for the ease of it, we use the official MQTT server Eclipse offers. So if it's a little bit slow, then it will be a little bit slow. So we've seen here something happened. He exposed an interface. So if we do our thingy here again, we should get a result again. So this time, the search came from here. You could see by, here, remotely he executed the search. And just by adding the one property for the remote service admin. So this is what we hopefully will get them to use for all the other stuff. So to finalize here, so everybody can go and have its break. If you want to try something like this yourself, like I said, this is based on our Gecko.io stuff. We have a workspace template for BND. You can use here, which gives you a prepared workspace with most of the R7 specifications inside it. It's like, a little bit like the old en route workspace, so you can just use it. We have an installer for it, a small how to use it, and all our other implementations that Gecko.io provides can be found under these repositories, but they will also be included in the template. So you can use the JaxRS Whiteboard, PushsStreams, whatever you name it, it should be in there working out of the box. The RSA is missing at the moment, so when the RSA is finalized, then this will be added at this template as well. So, thanks heaps for your attention, and
We are at break time, but if you don't mind.